questions about anything? I sent an email telling you the practice problems are on the home page. No questions? Well, at the end of last time, I stated this limit comparison theorem. And I thought I'd say a few more words about it before I move on to today's topic of limits of functions. So we're going to finally start doing calculus with functions. So there's the statement of the limit comparison theorem. It's about positive sequences, series of positive terms. So the coefficients, xn and yn, are sequences of positive terms. And there was a comparison test where we compared the tail ends of such a sequence. And if one sum was finite, then it converged, because the limit would be the soup. And you would compare those things, knowing the tail ends compare, and deduce convergence properties of one sequence from another. But this is a fancier version of that same thing. And so we assume that the ratio xn over yn, limit as n goes to infinity, exists. And that ratio of positive terms, the limit would have to be greater than or equal to 0. Okay. If it's greater than 0, that kind of means that xn over yn, they kind of look like a ratio r. So one would be r times the other, in the limit at least. And so the tail end of the series would do the same thing. If one of them was infinite, we'd expect the other one to be infinite. So they'd both diverge. And if one was finite, we expect the other one to be finite, which means they have to converge, because a sequence of increasing things bounded above has to converge. So in the case that r is positive, they do the same thing. In the case that r is 0, that means that if the sum of yn converges, that means the tail end of that series the terms get really small and add up to something finite. And if that ratio is 0, it means the xn's are even smaller than theyn's. So the intuition is that if yn converges, sum of yn converges, and of course the xn's are even smaller, they must converge too. That's the intuition. And there's not a reverse of that inequality. Knowing that xn's are really small wouldn't tell me anything about how small y's are in this case. And so it's a one-way implication. So r greater than 0 is the good case. We get both-way implications, but the r equals 0 case is only useful in case you know that the sum of yn converges. And I thought I'd say a couple words about the demonstration of this thing. So I'll call this an informal demonstration. Let's see. I'm thinking that xn over yn goes to r. Which is going to let me think that xn looks like r times yn. So if r is positive, that's going to mean that the tail ends are comparable by a ratio. The problem is that's a limit. And so if I want to estimate these things, I have to give them some slack. And here's the way to do that. Let's think. Here's the real line. let's do the r unequal to r greater than 0 case. And here's 0, and here's my r. It'd be nice if I could say that xn was r times yn. But, let's see, xn over yn is somewhere near r. And here's what I would like to be able to, I don't want it to get close to 0. And of course, I don't want that ratio to get too big. So where would I like it? When you think about stuff like this very long, you realize, oh, what the heck? Why don't I pick r over 2? So this would be the r over 2 side of that interval, and this would be the 3r over 2 interval. Okay. And so xn over yn is stuck in here somewhere eventually. And that's going to be a good thing, because then I'll be able to compare one side to the other. Okay, so the brilliant idea here is to let the epsilon be equal to r over 2 in the definition of limit. So there exists a natural number such that xn over yn minus r is less than this epsilon of r over 2. Okay, that's my epsilon. When n is bigger than or equal to n. Okay, I want to estimate, I want to play around and be able to write xn as something times yn, or greater than something or less than something. And so I'm going to write that absolute value inequality in its equivalent form of, let's see, that would be minus r over 2 less than something is less than 3r over 2. Let's see, I'm sorry, is less than plus r over 2. This would mean, here's the equivalent way to express that inequality. That's what it means for the absolute value of something to be less than something. It's between those two. Okay, that's an equivalent thing. And now when I get I want my ratio xn over yn. And so on this side, I'd have to add a plus r. I get r over 2 is less than xn over yn is less than 3r over 2. Okay. Whenever you can see something in a picture, you can monkey around and demonstrate it using inequalities. So I see that in this picture. The xn over yn is between r over 2 and 3r over 2. That's how you would show it formally, just using triangle inequality ideas. Okay, this is exciting because, let's see, let's think about these two sides of the inequality. What does this one say? This one says r over 2 times yn is less than xn. And therefore, I can deduce that if the sum of the xn's is finite, which means it converges, so the aha on this side, this implies if the sum of the xn's is finite, which means that the series converges, then r over 2 times the sum of theyn's would be finite. And so, of course, the sum of theyn's would be finite, and we deduce that the sum of theyn's converges. And it's using that left-hand inequality. Okay, so that's one of the directions. So check. And let's think about this one, this other one. This one would tell me that xn is less than 3r over 2 times yn. And so this time we would see that if yn converges, then of course the xn's too, because I could compare it by this ratio here. So the summation yn less than infinity would imply the same about xn, the sum of the xn's. Okay, so that's the if and only if convergence thing, all right? But then if you think about these inequalities, for example, if I know that the sum of the xn's diverges, that would mean that sum tends to plus infinity. Then the orange inequality, the right one, I could use that inequality to say, aha, theyn's do too, because I have an inequality there by a factor. Okay. And similarly, the other one implies that if the sum of theyn's diverges, then of course the xn's do too, because I can compare them by that, the purple inequality. Okay, so similar reasoning does the divergence case. That would be the summation of the those sums would be both infinity. The unbounded in the limit. Questions about that? Okay. I don't want to dwell on the special case of r equals 0 too much, but the case r equals 0 is even simpler, and you don't get as much in that case. But then you take, instead of taking the epsilon to be r over 2, which would be 0, and I wouldn't get anything in that case, I take epsilon to be equal to 1. And then I would get that xn over yn would be less than 1, less than or equal to 1, less than 1, for n bigger than or equal to n. And then I would get only one inequality, xn less than yn, for n bigger than or equal to n. And so, of course, if the sum of theyn's converges, then the sum of the xn's converge. And I don't get the other, I don't get anything else. Let's see. Oops, do I get something else? Maybe I do. No, that's all I get. I only get the convergence cases. Okay. So it's easier. But I only get a one inequality. I don't get two inequalities. So that's why there's only a one-way direction. Okay, well, it's important to understand the concept of that thing. Let me give you a couple of quick examples to show you how powerful this is. When you have to do very precise inequalities, like we did in the comparison test, it can get irritating. And you're kind of doing this same thing over and over again. And so, for example, if you look at a series like this, I want to compare it to something You have to think kind of hard to do it. But if you use the limit comparison test, you think, aha, that thing in the denominator, when I take the square root, is going to look like the square root of n squared, because n squared is much bigger than the other terms. And the square root of n squared is n. So we would do a limit compare with the sum of 1 over n. That one diverges, so the other one, so the one I wrote down would diverge. And let's see, how do you do the limit compare? I would take, what would be, I would take 1 over the square root of n squared plus n minus 1 divided by 1 over n. That would be n over the square root of n squared plus n minus 1. And then I would multiply the top and the bottom by 1 over n. Kind of thing you do in freshman calculus when you analyze these things. I take the highest power on both the top and the bottom, multiply through by that. That's multiplying by 1. And so when I get a big fat 1 on the top, on the bottom I would get, I'd put a 1 over n squared inside the square root. That would be 1 plus 1 over n minus 1 over n squared. And of course, as n goes to infinity, that would converge to 1 over the square root of 1 plus 0 equals a big fat 1. That's the r, and r is positive. So they either both converge or they both diverge. This is the famous harmonic series, so we know they both diverge. That's a p series with p equals 1. This 1 is the r. Questions about that? Another quick example is similar. Let's take a sum of 1 over n square root of n cubed plus 2n minus 1. Then the series to converge it, to compare it with, would be 1 over n to the 3/2. Because the stuff subtracting 2n minus 1 is small in comparison to n cubed. And so it's kind of, we see it would be minuscule in the limit. And so the tail end of that series acts a lot like sum of 1 over n to the 3/2. And that's a p series with p greater than 1. They both converge. I won't do that limit to do the limit comparison test, but it's a very similar calculation. Let's see, should I do it? What would I do? I'd multiply the top and the bottom by 1 over n to the 3/2 when I do the same thing. Anyway, it's fairly straightforward. Questions about anything? Okay, that brings me to today's topic, namely limits of functions. Of course, limits were invented by both Newton and Leibniz to study differentiable functions, derivatives, speeds. And so let's see, they both, Newton and Leibniz, and they were thinking about speeds. They took a difference quotient of a function and wrote down a delta distance divided by delta time. The delta distance looked like this, and the delta time looked like x minus a. Okay, so that's going to be an approximation to the velocity, and then they let this x slide into A and looked at those slopes of those tangent lines and said, aha, if they get closer and closer to something, that something is the instantaneous velocity. Okay? And so in trying to invent words to talk about this process, notice that this difference quotient is not defined at x equal a because there's a 0 in the denominator. Okay? So that's going to be part of the definition of limit. We don't care if the function we're dealing with is defined at the actual point. It's going to be what's happening for the function nearby. Okay? And so it took quite a few years to figure out exactly what it meant to be saying. You start using words like, oh, they get closer and closer to this limiting slope as x gets closer and closer to a. And that turned out to be too imprecise. It's hard to prove things using sort of axiomatic methods like geometry with that loose of a definition. So, after maybe a long time, tens of years, maybe 50s of years, the definition of limit as x tends to a of f of x equals L means think of epsilon as an error or a tolerance. So give me any old epsilon, no matter how small, there is a delta greater than 0. Of course, that delta might depend on epsilon. In fact, it probably does. So the book likes to write delta of epsilon, but it's traditional to get used to not writing that. Such that f of x minus the limit is within a tolerance of epsilon when x minus a is within delta. And here's a critical thing. Our thing might not be even defined at a, but it might still have a limit. So it's important to say here x is not equal to a. Then we can talk about derivatives. So that's important. And you remember from freshman calculus that there's going to be a word, f is continuous, if it has a value at the a that makes sense of that whole business. Then there's no jump at a. We'll talk about that later. Okay, so it's important to learn how to play around with this definition like we did with the sequence definitions. Let me do a quick example. Let's suppose C is a positive number. Show that the limit as x goes to C of x squared, you know from graphing x squared that it's nice and continuous. It doesn't have any jumps. So, of course, that limit is going to be C squared. I'm choosing this example because it's sort of the easiest one to show you how to play around with the epsilon delta definition of limit. Let's think about this for a second. Oh, here's the x, y axis. Here's a graph of y equals x squared. Here's a positive c. That would be c squared. So this is y equals x squared. And then I want to make my x squared within an epsilon, give me an epsilon bigger than 0, no matter how small. Okay, then that would give me a c squared, that's what I'm looking at, f of x minus c squared equals x squared minus c squared. Okay, if I look at that distance there, that would be the distance. Here's a plus epsilon. Here's a minus epsilon. Okay, this is epsilon here, this is epsilon here. And then if I stare at that for a second, I realize, aha, I can get a delta that gives me that tolerance. Well, I got to think about it. This is kind of a weird, that's probably fairly accurate. How weird that is. If I wanted to find the best possible delta to use, I can see it in that picture. In that picture, the best possible delta would be that little delta. But we don't have to worry about the best possible delta. We just want a delta. So here's, now I'm thinking too hard. What's the best possible delta? Oh, let's think about it. I need to find this spot over here, and so there's two spots I want to find. I want to find that spot and that spot. I kind of think my one to the right is farther off. Is that really true? Maybe my picture's crummy. You got to think about it. Let's see. Let's call this one x1 and this one x2. How would I figure out what x1 is? x1 x1 squared is equal to c squared minus epsilon. And so x1 would be equal to the square root of c squared minus epsilon. And x2 squared would be c squared plus epsilon. And so x2 would be the square root of c2 squared plus epsilon. And which one of those is farther away from c? I'd have to figure out which is bigger. I think I could do it. Which is bigger? Let's see. I'd have C. I guess I want to know which is smaller. Let's see. The C minus the square root of c squared minus epsilon, or the square root of c squared plus epsilon minus c. Okay, I can figure that out, I think, maybe. I might have to do some tricks. You know, like the difference of squares tricks? That would probably allow me to figure out which one is the smaller one. Anyway, that smaller one is the delta. Answer is equal to the best delta in the definition to take. Okay? But you don't have to do that much work. I just need a delta that works. Too much work. I just need I can, okay, so let's be lazier. In fact, I'm going to try to be as lazy as I can be. So let's see, what do I want to mess around with? I want to make x squared minus c squared small by taking x close to c. Well, if you ever did a difference quotient to see that something's differentiable, you realize, oh, I can divide by an x minus c in that difference quotient. And that's kind of what we want to do here. I can factor that as a difference of squares to x minus c, x plus c. And of course, that's equal to x minus c times x plus c. And this is basically my delta. That's going to be less than a delta. And I want this to be less than the epsilon I give. Okay. And so, in fact, what I really want to get is a bound on this. And it can be just a really crummy bound to bound this. By m. Some m. Who cares? It can be really rough. If I could bound that, let's see, I want it to be, yeah, then what would I pick? Then delta equals epsilon over m would give me what I want, Okay, and so let's think. I'm still thinking. I want to bound x plus c. That would be less than or equal to x plus my positive c. And so it'd be stupid to take a gigantic delta, because then x might get big, and I couldn't bound that thing. So if I go back up to my picture, my graph, there it is. Let's see. Let's think about my delta. If my delta is bigger than c, then I could get some negative x's. That'd be a pain. And so I think I should take my delta to at least be less than c. And in fact, if you start trying to think about what the best thing to pick would be, you realize you're thinking too hard. And so I would pick c over 2. I call it the c over 2 trick. If you did have to pick something, you might as well pick c over 2. Then this would be between 3c over 2. And x is sliding in there, so x could never get bigger than 3c over 2. Okay, so I'm calling this the c over 2 trick. I can start out by taking delta to be less than c over 2. Then my x would be under complete control. Then we see from the picture that c over 2 is, let's see, so remember I've got x minus c is less than c over 2. And that means that c over 2 is less than x is less than 3c over 2. And that's going to get, let me estimate this little thing right here. So x plus c, which is the thing I wanted to get a bound to, is less than or equal to x plus c, and that would be less than 3c over 2 plus c. That would be 5c over 2. That's the m. So if I'm in that interval, then I get my, taking delta, let's see, I wanted delta to be less than c over 2, but now I would also like it less than that m divided by epsilon. I'm sorry. So let's see, I wanted it to be less than c over 2. And once I have that, then I can bound that other thing, and I also want it less than epsilon over m, which would be epsilon over 5c over 2. Well, there's an easy way to do that. Take delta to be the min of those two things. Okay, so I'm just trying to illustrate that you can put in a whole lot of work trying to figure out the best possible epsilon, or you can be lazy and sloppy and just find an epsilon that works. That's the preferred strategy. And you'll find the book is often doing exactly that. Just finding one that works. And so part of it is saying, oh, I certainly don't want an x that's like 2,000 or something gigantic, because that would really botch up my estimates. So getting the x within some initial interval is a reasonable thing to do, and then maybe you need to shrink it. That's the philosophy. Questions about that? Well, let's see. In a fancier course on calculus, you start thinking about limits of functions on sets besides an interval. On subsets of the real numbers. And so here's the type of things you think about. Oh, here's kind of a dumb one. Let's think about, we have a function that's defined on, how about 0, a fourth, a half, three-fourths, and 1. There's no sense in thinking about limits when you have a function like this, because the x's never slide in and get close to anything. So there's no limits in sight. Resembling a limit here. Okay. But I guess we've seen plenty of limits. Let's see, when we look at sequences, if I have 1, 1/2, 1/3, 1/4, like 1 over n. There's 1 over 1, 1/2, a third, a fourth, etc. And then they start piling up at 0, and we expect those, they'd look weirder than that probably. That looks like a straight line. But 1 over n goes to 0. And so there is something looking like a limit here. Limit of 1 over n is equal to 0. And we do see something sliding into the origin. There's a word for that. The things are piling up. The 1 over n's are piling up. This is not a mathematical term. At x equals 0. There's a fancy mathematical word for that. X equals 0 is called an accumulation point. Accumulation point of that set. Notice that it's not in the set. Things can pile up there without being, and that point doesn't have to be in the set. And notice there's always infinitely many if you're talking about piling up. So even if I put a very small interval about 0, there would still be infinitely many points in that set. And that's kind of a feature of the definition. Let's think of another example. Let's take the set of S to be rational numbers. Then all the stuff we played around with earlier in the semester, we know that the real number, square root of 2, is an accumulation point. I can find rational numbers in there that are arbitrarily close to the square root of 2. Okay, so let me now write down the formal definition of accumulation point. So S is a subset of the real numbers. X naught is an accumulation point. Sometimes those are called a cluster point. If in any epsilon bigger than 0, let's see, I want to make sure I use the same word. Delta. Any delta bigger than 0, I was tempted to say epsilon. No matter how small, there's a point in S little s and capital S with S different from X naught. Such that S minus X naught is less than delta. Okay? So that just means the points in S pile up at X naught. I can always find one close by, no matter how small that little delta is. And it's an easy thing to check. if x naught is an accumulation point, of S, then if I look at a little, let's see, this is the book's notation, V sub delta of x naught. That's the interval of, for radius delta about x naught. Infinitely many. S in S with S unequal to x naught. No matter how small the delta is, for any delta. Okay, so remember what V sub delta is. Here's x naught. The delta would be the little open interval. This is x naught minus delta, and this is x naught plus delta. Okay, so I claim there's infinitely many things piling up there. Let's see, how would I demonstrate that? First, I'd tell you delta equal a half. Then I'd find you a blue line there, an S. Then I'd tell you delta to be a fourth. I'd find another S. Well, let's see, I'd take my next delta to be so small that S is not in it. And then I'd pick another S that's different from my first S. And then I'd pick the next delta to be the one to make that distance so small that the previous two S's aren't in it. And I keep doing that forever. I get a sequence. Okay. So here's why. Take delta to be 1. I'd get an S1. And then I would take delta 2 to be equal to S1 minus X naught. Then I'd get one inside there, and that would be my S2. And of course, it'd be different than my previous one. And I keep doing this. So the next one would be to take delta 3 to be equal to S2 minus X naught. So it's smaller than all of them. That's a decreasing sequence, etc. I get a sequence, in fact. I get infinitely many SNs. They're all different than, let's see, I needed, I would take an S1 unequal to X naught, and I'd get an S2 unequal to X naught, etc. And I'd end up with infinitely many S's that way. So they pile up there in the sense that well, let's see, I'm kind of running out of time. Any last minute questions about anything? Okay. Homework 6 is due on Wednesday night.